Welcome back. Ever feel like
You're staring into the abyss of knowledge, wondering just how much we can know about these.
complex systems swirling around us?
Today, we're tackling that very question,
Okay.
diving headfirst into the
And
fascinating.
sometimes brain-bending world of undecidability.
You sent in this paper by Prokopenko and colleagues.
Right. It connects this idea of undecidability
Uh-huh.
to everything from the logic puzzles that keep us up at
To
night
the very fabric of computation itself.
through this mind-bending landscape.
Yeah.
So before we get lost in the weeds of formal systems and Turing machines,
Yeah.
can you set the stage for us? What does undecidability actually mean
Yeah.
in this context? Is it really as hopeless as it sounds?
It's not about hopelessness, but rather recognizing there are some fundamental limits to what we can definitively spiri no W. Even in systems we think of as predictable. Imagine posing a question, a perfectly clear question, but any algorithm, no matter how cleverly designed, can guarantee a yes or no answer. That's undecidability in a nutshell.
Okay, I'm already intrigued, but my brain loves a good example.
What really caught my eye in this paper was the mention of the liar paradox.
Right.
The whole "this statement is false" dilemma.
Yeah.
How does that tie into something as complex as, say, computer science?
That's the beauty of it. The liar paradox, with its self-contradiction, highlights this idea of self-reference, which is surprisingly central to undecidability across multiple fields. Think about it. The statement refers to itself, creating a logical loop we can't escape. And this self-referential trickery isn't confined to logic puzzles. It pops up in how we write code, how certain computer programs behave, even in those mesmerizing cellular automata patterns.
Hold on, we'll get to those mesmerizing patterns soon, I promise.
But first, let's unpack this idea of formal systems.
Okay.
I have a feeling that's a key piece of this puzzle.
Walk us through it. What are we talking about when we say formal system?
Imagine a kind of structured language for reasoning. We start with axioms, your basic building blocks of truth, kind of like the rules of a game. Then, using strict rules of logic, we derive theorems, those aha conclusions we reach. Like in geometry, you have axioms about points and lines. And from those, you build up theorems about triangles and circles.
So far, so good. Where things get really wild is when we realize that these formal systems, these rule-based structures, can be used to talk about themselves.
Okay.
And that's where Gödel's incompleteness theorems come in.
Okay, two questions.
1. How W can a system talk about itself?
That already sounds like we're bending the rules of reality.
And 2, why are these incompleteness theorems such a big deal?
Let's tackle them one at a time. Gödel's brilliance was figuring out how to make a formal system refer to itself indirectly, using a clever trick called Gödel numbering. It's like assigning a unique code to every statement within the system. This allows statements to reference other statements through their code, creating a kind of self-referential loop.
So it's like a secret language within the system, where statements can subtly point to each other.
Precisely. And here's the kicker. Gödel proved that within any sufficiently complex formal system, there will always be statements that are true but unprovable within that very system. Imagine trying to create a dictionary that defines every word. Including words like define, you inevitably hit a wall.
So even with perfect logic, we're always going to bump up against some truths that are just out of reach.
That's both frustrating and fascinating at the same time.
Absolutely. And this concept of undecidability isn't limited to these abstract formal systems. It bleeds into the very heart of computer science, particularly when we start talking about algorithms and the machines that run them. Which brings us, of course, to the infamous Turing machines. A Turing machine, at its core, is a theoretical model of how we compute. Picture a device with an infinitely long tape, a read-write head, and a set of simple rules dictating how it moves and changes symbols on the tape. It's essentially a blueprint for any computation you can dream up.
Like a very, very patient robot with a typewriter following instructions one symbol at a time.
A very simplified analogy, but I appreciate the visual. Now, one of the most famous examples of undecidability in this realm is something called the halting problem. Imagine you've written a program and you want to know if it will eventually finish running, or get stuck in an endless loop. Turns out there's no single algorithm, no magical program that can answer this question definitively for every possible program.
Wait, so even with something as seemingly structured as computer code, we hit these walls of unknowability.
Exactly. And the reason this happens loops us right back to that concept of self-reference. Just like with formal systems, a Turing machine can be encoded as data that can be fed into another Turing machine. Essentially, you're asking a machine to analyze itself, leading to the same kind of paradox we saw with the liar's paradox.
Okay, we're starting to see a pattern here. Self-reference leads to undecidability. It's like the universe's way of saying, nice try, but you can't outsmart the system. But if it's everywhere, from abstract logic to the code that powers our world, where else does this pop up?
You're catching on quickly. This mind-bending connection extends even further into the captivating world of dynamical systems. These are systems that evolve over time according to a set of rules. Think about things like the weather, ecosystems, or even the stock market.
Okay, you officially have my attention.
Dynamical systems. I can already sense we're about to go deep down the rabbit hole.
Cellular automata, or CAs,
Yeah.
are a fantastic example of how undecidability plays out in dynamical systems. Imagine a grid of cells, each following a simple set of rules, like if a cell has two neighbors, change its state, otherwise stay the same. Despite this simplicity, CAs can produce incredibly complex and often unpredictable patterns.
It's like those screensavers from the 90s, but with a hidden layer of mathematical magic.
What's fascinating to me is that we can actually create universal cellular automata. What does that even mean in this context?
Just like a universal Turing machine can simulate any other Turing machine, a universal CA can simulate the behavior of any other CA. It's like finding a single Lego set that can build any other Lego model, no matter how complex.
So within this grid of cells, with just a few simple rules, we can actually embed the logic for universal computation.
Imagine this. Certain patterns within the grid act as signals or data, while other patterns act as the program manipulating that data. By carefully structuring these patterns and how they interact, we create a CA capable of carrying out any computation a traditional computer could.
So we've gone from self-referential statements in logic
Right.
to self-referential programs in Turing machines.
To self-referential patterns in a grid.
It feels like we're uncovering some deep underlying principle here.
Well, exactly. And just like with the halting problem for Turing machines, we encounter undecidable questions about these universal CAs. For example, given a starting pattern, will it eventually stabilize? Or will it keep evolving forever in unpredictable ways? We might not be able to determine the answer, even knowing the CA's rules.
It's like that saying, life is like a box of chocolates. But here, it's a grid of pixels with the potential to unlock the secrets of computation. What's even more intriguing is this idea of the edge of chaos.
How does that tie into all of this?
It's at this boundary, this edge of chaos, where systems are complex enough to exhibit incredibly rich and unpredictable behavior, yet not so chaotic that they descend into pure randomness. Think of it as that sweet spot between order and utter unpredictability.
So it's not just about things being utterly unknowable. It's
Right.
about this fascinating dance between structure and surprise.
But it feels like we keep coming back to this idea of self-reference, this
Yeah.
ability of a system to, in a sense, refer to itself. What is it about this self-reference that seems to break our neat attempts at prediction and complete knowledge?
That's a question that has puzzled mathematicians and computer scientists for decades. It all circles back to the limits of what we can describe within a formal system. Imagine creating a catalog, a complete inventory of every possible thing, including the catalog itself. The act of including the catalog in itself creates a kind of paradox, a wrinkle in our neatly ordered system.
So it's like trying to draw a map that includes itself, or holding up a mirror to another mirror.
It creates this infinite regress, a hall of mirrors we can't escape.
Precisely. And that's essentially what's happening with self-reference in these systems.
Hmm.
When a system can refer to itself, directly or indirectly, it breaks free from the constraints of simple categorization. It introduces a kind of circularity that our traditional methods of analysis struggle to handle.
And it's in this breaking free, in this embrace of circularity, that we find the potential for incredible complexity and ultimately this fascinating undecidability.
Yeah.
But I have a feeling our listeners are itching for more.
What are the implications of all of this?
Why does understanding undecidability really matter?
It might seem abstract at first, but understanding undecidability changes how we approach knowledge, prediction. Even the very nature of reality. It's like realizing that the universe is far stranger, far more nuanced than we could have ever imagined. And that, my friend, is a truly exciting thought.
I am so with you on that. But let's dive deeper into those implications,
Ah.
because I have a feeling this is where things get really interesting. And we're back diving headfirst into those implications.
Okay.
Because I have a feeling This is where things get really interesting.
Right.
Before, you mentioned that this concept changes
Uh-huh.
how we approach knowledge itself.
Yeah.
I have a feeling this goes way beyond just saying,
Well, some things are unknowable, so why bother?
yeah, it's more about recognizing that our quest for knowledge is an ongoing journey, not a destination. Undecidability reminds us that there are inherent limits to what we can know with absolute certainty. Even within systems we might assume are deterministic, it's a humbling realization,
Right.
but also incredibly liberating.
Liberating.
Yeah.
Help me see the bright side here.
Why should I be excited about bumping up against the limits of what we can know?
Because it means the universe is far stranger and more nuanced than we might have imagined. It means there's always more to explore, more to discover, even within the realms we thought we understood. Think about the implications for scientific discovery. Instead of assuming we can predict and control everything, undecidability encourages us to approach the world with more humility and curiosity.
So it's less about finding the right answer,
Yeah.
more about asking the right questions.
Embracing the unknown
Right.
and being open to unexpected possibilities.
Exactly. And this has huge implications for fields like artificial intelligence. One of the holy grails of AI research is to create machines that can think and learn like humans. But if human thought itself is shaped by this inherent undecidability, it changes how we approach building truly intelligent systems.
Instead of trying to program machines with all the answers,
Yeah.
we should be teaching them to navigate uncertainty,
Uh-huh.
to learn from their mistakes, to evolve their understanding over time.
Precisely. Instead of seeking perfect solutions, we might focus on creating AI that can adapt, explore, and even surprise us with their creativity. It's about embracing the edge of chaos, that space where complexity and structure collide, where genuinely novel solutions often emerge.
Now that is a vision of AI that truly excites me.
Not a cold, calculating intelligence, but a flexible, evolving one that works alongside us, not just for us.
Right.
You've given our listeners a lot to chew on today.
I hope so.
What's one question, one lingering thought?
That you hope our listeners will take away from this deep dive into the world of undecidability.
If undecidability is woven into the fabric of computation, from the abstract systems we've discussed to the very cells in our bodies, could harnessing this principle be the key to unlocking new forms of creativity, problem solving, even consciousness itself?
And there's something to ponder.